Again, hello all, and welcome to 2020, spring Starry Night show number 7. And again, we have lots of people here, great panelists. We have Alex, we have Ivan, we have David, we have Yannick, we have Chris, we have James. Uh, so again, we try to talk about 4 problems. And I think today's question might be pretty hard. If we cannot finish, we do only 3, then it's fine too. We can finish them on Friday. The first question is actually quite classic. I want to use this opportunity actually talk about a paper by a great mathematician. He's John Conway, and it pays tribute to him. He just passed away 2 or 3 days ago. I think it's 2 days ago, or 3 days ago now.
Saturday.
Right? Yeah. Due to the virus, John Conway is a great mind, and he invented the wonderful game of life, and he do great research and also give lots of talks to promote wonderful math ideas. So the first question we are going to talk about today actually has a very nice solution in one of his recent talks. And I'm going to mention this problem, and Chris we're going to give a first proof, and then I will also mention Professor Conway's paper, and then talk about the proof he mentioned in his proof, in the article. So the question is actually quite classical. It's about square root of 2 is an irrational number, right? And that thing, I think many of our audience knows what's the proof. The classical proof is to what? Write root 2 as m over n, and do something about this. Should I change to my screen to the camera? Okay, let's do that. So square root of 2 is irrational, right?
Well, we need to prove it.
Well, we need to prove it, right? Yeah. So that's a very classical problem, and by historical thing, people attribute this to, I think, to Pythagoras, right? And that's leading to the understanding that there's irrational numbers. So in many algebra book or many proof books, people start by saying this root 2 is m over n for some reduced fraction, and then square, talk about the divisibility, and then you basically try to show that we start with the assumption that m and n are co-prime, but somehow both of them are divisible by 2, so that's contradiction, and then so on. In this proof, there's a little tricky thing always make me feel unease. The issue is about this, what I call we use the fact of this a lot. So 2 divides some number product A and B, and we have to use this to show 2 divides A or 2 divides B. And this is something actually I think all our students knows by heart, because this is one of the most important properties of what? Prime numbers, right? But actually, I'm pretty sure our audience, those young, people interested in math, hardly know why this is actually true, this property, right? Because the prime, a number being prime, only tells you 2 has 2 divisors. Any prime, 1 and itself, right? So P divides AB tells you P divides A or P divides B are completely 2 different things. But somehow, when we do learning the beginning of number theory, we basically treat them basically the same. We basically immediately use them, right? So somehow all these proofs involving some kind of, what do you call, fundamental theorem of arithmetic about prime factorization. right? And as for students who are going to do more higher mathematics studying, they should realize as soon as we are talking about different number fields, then these two definitions are not the same thing at all. One is being irreducible, one is being unique factorization. So that's very, very different things. And that's basically the beginning of algebraic number theory, right? So that's why this proof always have something in there that is not completely what? Satisfactory. So we are talking about two geometry approaches that make this more clean, okay? The reason is this, in the proof of this property, somehow we have to use this so-called Fermat's infinite descent. And the geometry proof basically directly shows the descent immediately without going through this. So that's why it's more visualizable. It's helpful, right? So Chris, you want to go over the first proof you were talking about?
Sure. So Ivan, if you can put up the diagram that I drew, and I'll talk through it so that we can mark things off as necessary.
Mm-hmm. Okay.
Can I see it? Oh, yes. Okay. So this proof, which I heard of about 10 years ago. So we're going to assume again by contradiction that root 2 can be expressed in the form a over b, where a and b are integers. Of course, a and b are positive integers, and a has to be greater than b because root 2 is greater than 1. Now, there's a lot of choices we could pick for a and b. Like if any, a and b satisfy that equation, I could take any integer multiple of a and any integer multiple of b, and I'll still have that ratio. So in particular, I'm going to focus on, let's think about the smallest a that would work. It's easy to convince yourself that a equals 1 can't work, but there's going to be some smallest a, that will do the trick, supposing that root 2 were rational, okay?
Mm-hmm.
And so what I've constructed here is a circle centered at point O, and its radius, OA, is equal to B. And then I've constructed at the point through point A, the tangent segment to the circle, and I make that also of length B, so that because we have a right triangle and two legs of length B, it's a 45, 45, 90 triangle. And because the circle OA, of course, is, OB is what? B root 2, which is also equal to what? A.
Mm-hmm.
And A and B are integers again, by assumption. And then OA prime, because it's a radius, is also equal to B, right?
Okay, so let's stop here. Maybe even our panelists who'd never seen this before, they can think, what's the point of this A prime?
Yeah.
I'm guessing that you're probably going to look at triangle B, A prime P, and contradict minimality of A somehow.
Yeah.
So wait, David, what do we know about this triangle B, A prime P?
Well, you know that OA prime is perpendicular to A prime P because that's a tangent. So triangle BA prime P is also a 45, 45, 90. So because BA prime is equal to A minus B, you get that A prime P is also A minus B. And so BP is going to be square root of 2 times that. But you know that square root of 2 is equal to A over B. And that probably gives you a contradiction somehow.
So wait, you want to show that BP is an integer, right? If you show it, then I think you're good, right? How do you show this?
Well, what else is A prime P equal to?
Wait, you know that BP has to be rational, right?
Mm-hmm. Yes.
Why?
Because by power of a point from B to A P A prime O. But that's just my thought.
And
that's a
alternatively,
little bit,
it's similar triangles, right? If we're assuming that B over A is rational, then so must BA prime over BP, and you know BA prime is rational, so there you go.
PA equal to PA prime because equal tangents, right? That's
right.
Yes.
So
wow.
we get by subtraction that BP is just what? B minus A minus B, so 2B minus A?
That contradicts minimality.
Yeah.
Right. Because, again, A is greater than B.
Right. So now root 2 is equal to what? Ivan, I don't think people can see that.
Yeah,
you want to write
move it to the right a little bit.
Okay. Let's go here. So this is a smaller triangle. Can I write this way or what?
Just write on this side, on the other side. Under
suppose A is the smallest integer.
Yeah. So basically root 2 is equal to 2B minus A over A minus B, right?
Yep.
Yeah.
And that's smaller.
Yes, and 2B minus A is smaller than A.
Yeah, because B is smaller than A, right?
Right.
And you have contradiction.
And this is, as Zuming said, an example of Fermat's principle of infinite descent, which, for those who aren't familiar, you can't have an infinitely decreasing sequence of positive integers.
Right.
So we've constructed a smaller triangle that has all integer lengths that where we have this root 2. So that's our contradiction.
Yes. So this is very good. This still use lots of knowledge, actually. Equal tangents, similar triangles and so on, right? So now I'm going to switch to mine. Okay, so we are going to talk about this paper. Why I say I make a contribution, not a contribution, in tribute to Conway, because I learned that this one from Conway's paper. Okay, and he gave a very nice talk at Cambridge University. He called it The Power of Mathematics. In this one, he explained 3 examples, and the first 2 I will explain. The first one I will explain here, and the second one I will explain next time. And the last one is on knot theory, which I don't have enough expertise to explain, but I give you guys a guide for your future study, right? So now let's focus on this one. Ivan, can you ping it to my stuff? Okay, right? So I labeled this, okay, for you guys to, in the case you want to find this paper, you can Google it very quickly. Now, his proof is based on another mathematician, and his name is, I put it here. I think you can see this article and get this paper somewhere over here. I was able to see it. This is the original author of this, okay? So the new proof actually is extremely even more simpler. Is basically we just draw 3 squares. So this is also, so root 2 is m squared over n squared. So again, we are talking about minimality. So let's say m plus n is smallest. Or we can say m is smallest. Either one of them is fine. Okay, either one of them. Okay, you can choose either one of them. So now 2, we right? Basically,
it's 2.
2. Sorry, 2. Right? So you have a square, m squared and n squared. What we know is m squared equal to 2n squared. Okay, that's what we are given. So the next thing is I just draw this picture and see if you guys can get it. So I still draw m squared. I put n squared here, and I put n squared here. Oh, I didn't draw this well, sorry. Let me redraw. Do you guys see the trick? The trick is about these 3 squares. What can you say? Note this, n squared plus n squared is m squared, right? This is what is given. So that means the area of this square and the area of this square add up to area of this square. So now if we tile this square this way, what can you say?
Can you say the same thing about 1, 2, and 3?
Yeah.
Like the overlap, like you know that n squared plus n squared. So the area of the two big squares is equal to the whole thing, which is equal to 2 equals 1 plus 3. Yeah, because you can take the stuff from 1 and 3 and smush it into 2, and you've covered the same area.
Exactly, right? Because if you want to add this to area, it should be the whole square, so the only overlap part should be distributed to here, right? So we get this. And clearly 1 is equal to 3, right, by symmetry. So now we already violated the minimality. Now we have another square is the sum of these two, equal 1. So what's the dimension of 2? Dimension of 2 is basically 2n minus n, right? Equal to some other 2 squares. Say this is some k squared. And now you have something smaller. So 2 is equal to 2n minus m squared over k squared.
Well, k is what? M minus.
Well,
n.
k is 1 and 3, right? Well, yeah, you can get k also. K is what?
M minus n. It's
minus
exactly
n.
what in.
This is exactly what Chris over there, right? Of course, they have to do the same thing, right?
Yeah.
Right? Okay. So let's stop at here. So we move on to the other one. The next time we will talk about his article is about this wonderful, very difficult theorem. It's called Moray's theorem. And how does he prove it by just drawing some picture? Okay. So you guys can, if you want to think about it, and let me use 1 minute to tell you what is the theorem about. You have a triangle. If you trisect it, those are trisection. No matter what the original triangle is, these 3 points form an equilateral triangle. This is quite hard to prove, but Conway has a very, very nice way, and he introduced in this paper also. So when you guys read this paper, be careful. He skipped a few important parts that you should ask your question, and then we can talk about how to read math papers in the future. Okay, that's it for me. So yeah, Ivan, you have the floor.
Oh, well, it's not actually me, but I suggest we go directly to the next question. And it is the following. It is number theory. And I think we need a few minutes to understand what it says.
Okay.
So basically, it's not my question. It's one of the attendees' questions. And for any two positive rational numbers,
one of the attendees' questions. So that means we need to take a poll on who proposed the question then.
Okay, I will run the poll. Let's read the question first. So I think you have two fractions a over b, c over d. These are rational, that form two rational numbers, such that GCD of a and b and GCD of c and d is 1. We can define their greatest common divisor in the following way. Okay? And for a positive integer k, let f of k denote the number of ordered pairs of rational numbers, m and n, while m and n are between 0 and 1, such that GCD of m over n is equal to 1 over that number. And then what is f of 2017 minus f of 2016? So I can run the poll. Meanwhile, you guys can try to understand the
poll. The author, the poster, give a very special definition of the GCD of two fractions, right? Because we know the GCD of two fractions cannot be easily well defined instead of, integers.
Wait, I thought the question was by an attendee. That's why I was interested in doing the poll.
No.
Now you're allowed to participate, yes. But let's see, what is the GCD of 2 over 5 and let's say 3 over 7? How do you do this? This GCD is going to be GCD of
14 and 15
14 and 15 divided by 5
times 7.
7, which is 1 over 35. Okay. So you guys see we have this one. Maybe we need to understand how do we get this one.
Yeah, can we close the poll? Let's move on. Yeah, I think our audience is quite correct. Is David's question? The audience won by 1 vote, 6-5 over Evan. Okay. Okay. So now
if you're gonna guess 2 people, guessing either me or Evan is probably not a bad choice.
Evan's not even here. Oh, wait. Well,
Yeah, that's why I guessed Evan. I thought it was by an attendee, so I thought maybe Evan was secretly attending. No one else there was attending.
let's see.
A panelist.
Okay. Well, you're also participating.
Yeah, attendee.
Okay.
All
So,
right.
David, maybe you can share the screen and guide us. How did you come up with this problem?
Yeah, so normally when I talk about problems, I talk about both how I came up with the problem and how how you solve it. But in this case, it's sort of interesting because the way that I solved it is very intertwined with the way I came up with it. So I want to instead just talk about how my process in terms of coming up with this whole problem. So let me share the screen again. Give me a sec. Oh, the host has spotlighted my video for everyone. Okay, cool. Before I do that, let me stop the video because yeah. So I think the original motivation for this problem should be not too difficult to come up with. You have 2 rational numbers. First off, can everyone still hear me?
Mm-hmm.
Okay.
Yes, but I don't see anything.
Do you have my screen up?
Nope.
Nope.
Okay. Oh, I guess I need. Oh, okay. I misinterpreted the prompt. My bad. I actually still need to share the screen. Okay, cool. So we have the GCD of 2 rational numbers, and we want to do something with it. So the way I came up with this problem, sometime in my freshman year. Okay, the summer after my freshman year of college. This was before I was off to do some stuff at Austin Math, so I had about a month back at home to just sort of do whatever I needed to. And it basically stemmed from asking the following question. Well, sort of obviously, what happens? How can you define the greatest common divisor of 2 natural numbers? Sorry, 2 fractions. Because it's not obvious how to take the greatest common divisor of 2 fractions, as Zooming said. But fortunately for me, that question had already been answered. In fact, I found the response. Did my screen sharing get stopped somehow?
No.
Oh, I can resume the share. Oh, okay.
No, I see it.
Yeah, no, sorry. The screen sharing isn't quite working the way I want it to. Give me a second just to sort of get stuff pulled out. I wanted to do something a lot cooler, but it turns out that the way that I'm doing this isn't quite working. So give me a second to just get stuff sorted out. Yeah, there we go.
Okay.
The point is that, yeah, I found the right thing to do on a Tumblr post, which is probably the first time I've ever said that. So this Tumblr post has the greatest common divisor of 2 rational numbers. And it gives this definition right here. The greatest common divisor of 2 rational numbers a over b and c over d is defined to be literally the exact thing in the problem statement. Mm-hmm. So the point is, this definition is not mine. I saw this definition while attempting to do some research. But I found this definition to be suitably interesting that I decided, okay, maybe I could do something if I just played around with this thing a little more. And the reason I bring this up is because of this next part. This Tumblr post actually proves an important part about the GCD. It retains its multiplicativity. Now, what do I mean by this? In the integers, if I take two integers and I multiply them by 2 and I take their GCD, that's the same thing as taking the GCD and multiplying it by 2, right? Mm-hmm. And this thing tells you that this is multiplicative. So what does multiplicativity tell you? It says, and this is the first thing I realized, that if I want to compute the GCD of two, let's say if I want to compute the GCD of two rational numbers, then I can sort of do this scaling trick and pretend that if and only if the GCD of A over BM, C over DM is equal to 1. Something like this. The point is, once you have multiplicativity, if figuring out the greatest common divisor of two numbers, so figuring out the GCD of two fractions, is essentially equivalent to determining whether the GCD of two fractions is 1. Because if I can come up with a criterion for determining whether two fractions are relatively prime, I can multiply that by any suitable rational number and get a criterion for determining whether the GCD is any number I want, just by multiplying by a suitable constant. Mm-hmm. So this raises an interesting question. When are two fractions relatively prime? And this is the first thing I decided to look at. So when are two fractions relatively prime? That's a very interesting question. Well, let's actually play around with this for a little bit. Suppose I have the GCD of A over B and C over D equaling to 1, right? We don't know how this works, but we do know that this is equal to the GCD of AD and BC over BD, right? So if this GCD is 1, then this tells us that BD is equal to the GCD of AD and BC. Okay, so now let's think about what this means. What this tells us is, among other things, that B divides the GCD of AD and BC. Right?
So B divides AD, right?
Correct. So
and
if B
A
divides
and D are co-prime, so B must divide D, right?
Correct.
And in the same symmetrically, D divides B. Okay, makes sense.
Hold up. Let me just make sure that I've got my bearings straight, because give me a second. I'm pretty sure this is right. I just want to make sure that it's right.
Yeah, this seems fine.
Yeah, this time.
Give me a second. Archive.
But it looks very complicated, Dave.
Yeah, I'm just the point. There's a punchline to this. There's a punchline, just like there is with every single problem. I'm trying to make sure I get the right punchline.
So D must divide B. So B and D must be equal. So B squared is GCD.
Oh, I actually did this. Okay, that's why I'm doing this. I'm doing this differently. I'm doing this differently. We're gonna get rid of the condition of the relatively prime because it really doesn't matter.
Okay.
The condition that A and B and A over B and C over D are relatively prime doesn't actually matter because of multiplicativity. I just put it in there so we didn't have to worry about whether or not it was well defined in the problem statement. But what does this tell you? This tells you that I'm just going to say that AD is a multiple of B. AD is a multiple of BD. So AD is equal to BD. AAD. Wait, shoot.
BD.
Yeah, BD. There we go. That's more like it. Okay. So AD is equal to MDB, and furthermore, we know that BC is equal to NBD, where M and N are positive integers. Because now we're working in the relatively prime case for integers.
Mm-hmm.
And what this tells us is that A over B equals M. And C over D equals N. So in other words, these things were just relatively prime positive integers.
Mm-hmm.
Meaning that we kind of gain nothing non-trivial by moving to the GCDs of fractions. It's just two fractions are relatively prime if and only if they're integers that are relatively prime. And so this actually gives us a complete description of the thing in the problem statement. This tells us that if GCD of P and Q is equal to 1 over K, then that means I can write P as A over K and Q as B over K, where the GCD of A and B is 1.
It's because of multiplicativity, right? You multiply by K, then KP and KQ must be two integers.
Yep.
Yeah, makes
exactly.
sense.
So that's exact. And in fact, we can check that example that you constructed. Because what were the numbers? 2
over 5 and 3 over 7, yes.
2 over 5 and 3 over 7, that's equal to 14 over 35, and 3 over 7 is 15 over 35. So this completely is consistent with the thing that we've come up with. Because the GCD is 1 over 30, these integers can be written as two relatively prime integers divided by 35, and their GCD is 1 over 35.
Mm-hmm.
The point is, what is this problem telling us? So how can we generate two rational numbers whose GCDs are 1 over K? Well, this means, then I can write this as, so that means that f of K is equal to the number of pairs of relatively prime integers less than K, such that GCD of A and B is equal to 1. Right? Does that make sense? Or did I skip too much there?
Yeah.
Okay.
Makes sense.
So this would make an amazing problem asking people to compute f of something, except we have a slight problem that this is impossible to compute. It's absolutely ridiculously impossible to compute this by hand. So I had to salvage by looking for this difference. That's the only reason f of 2017 minus f of 2016 is there. I had to put that in the problem to make the answer computable by hand. Why? Because you can sort of think of this combinatorially. F of 2017 and f of 2016 are both counting the numbers of ordered pairs. So f of 2017 is equal to the number of AB at most strictly less than 2017, which are relatively prime. And f of 2016 is equal to the number whose GCDs are relatively prime. So notice that this subset over here is contained inside, other way around. the subset on the top.
But that's why
I
you
wrote
the difference. Yeah, okay.
I think I wrote that backwards, right? Yeah,
Yeah.
it doesn't really matter. But so the point is, that's why I took the difference. Because what is the difference representing then? What precisely which pairs are counted in the top set that are not counted in the bottom set?
Well, one of them must be 2017, right?
Off by
or
one,
16,
2016.
16.
Yeah.
It's a strict sign, correct.
Yep. So that
So
means that
you
f
need
of
the prime factorization of 2016.
number of A, B, with one of A or B equal to 2017, because clearly you don't need 2016. Because clearly you don't need both.
2016.
Yeah. Clearly you don't need. Clearly, if both of them are 2016, then GC is not going to be 1, such that the GCD of A and B is equal to 1.
And I hope.
And what's that number?
Yeah,
well,
people in the audience know what is it. It's the famous function, right? It's called Taussian function, right?
So the answer is 2 times, because you have to count A and B separately, the Euler phi function of 2016.
Mm-hmm.
Which you can compute that to be, I don't know, I think it's 1,152, but I'm not positive about that. Someone should check that.
That sounds right.
You can divide out a lot of twos.
Yeah, fortunately, this was back in 2017. So people who were taking math contests in 2017, this was in January of 2017. So people probably still had the prime factorization of 2016 memorized.
Yep.
Nice.
So
okay.
that's the. I'm gonna just briefly summarize what happened here. This is basically
David. I think it's clear, and our students can get the idea what is GCD of two rational numbers. When it's 1, they should understand it's all about being integers.
I was going from a different direction. So what did I do? I came up with a question. I looked in the literature to see what had already been answered, found some useful information, and tried to expand on that information. And eventually, by expanding on that information, I found a good problem to ask. Mm-hmm. And it was just through like some massaging of the problem statement that I got exactly what I wanted. Mm-hmm. So that's very similar to how research works.
Nice.
So yeah, you could say that problem writing is just mini math research in some cases. All right, that's all I got.
Okay, we have like 20 more minutes, and we have 2 quite challenging problems ahead of us. So we need to choose.
Let's just focus on what James's question. That's complicated.
Yeah, let's do that.
Yeah, so we can just finish this one actually. So I know you guys are probably tired about discussing it.
Yeah, we have already spent two.
It's okay.
Meetings.
To be fair, I didn't intend for this to be longer than 1 session. In fact, I came up with the other versions during.
Yeah, this is great.
I came up with it during literally during the session last time. So anyway, to recap, so it looks a little different now. I just kind of simplified it. I also changed the dimensions to 300 by 300 so we don't have to worry about certain issues like not being divisible by 3. Essentially, what happens is we're coloring the cells of a grid red or blue, and each red cell, you guys can see my screen, right?
Mm-hmm.
Yep.
Okay, each red cell is adjacent to at least 3 blue cells, and each blue cell is adjacent to at least 2 red cells. So last time we already established that the minimum number of red dominoes is in the equality case is when 2/5 of them are red, and we have a certain diagram. I think I have a pointer actually. I'll use my pointer. Is up here. And we have basically just a pattern that's modulo this square of area 5 that's kind of tilted. So basically this pattern just repeats modulo the square. We get this kind of cool pattern that whose goal is to minimize the number of red-blue dominoes while maintaining this condition that there must be a decent number of red-blue adjacency pairs. So I also decided that there are 2 more questions that you can ask that are pretty interesting about this diagram. One is find the maximum number of possible red cells, and it turns out that actually there are a bunch of equality cases. So we kind of will dive into that. and the third question you can ask is to find the minimum number of red cells. So so this is something. So those 2 and 3, you could probably is a lot easier than 1 in terms of finding what you think the answer can be. So half of the problem, maybe not half the problem, but the first step of the problem is to kind of like find what you think you want to prove first before you actually go about proving it. So as Alex mentioned last time, his guess is that 2/5 is really close to 1/3 and 1/2. Therefore, we probably have 1/2 for the second part and 1/3 for the third part. And I guess this is the kind of intuition that gets you 5 gold medals at IMO. I don't know. I wouldn't know, but it seems correct. And if you play around with this, this is what you end up like finding. You end up finding, oh, this is probably true. Now we have to just prove why it's true. So you think this is half red, and you just play around. You're like, oh, I want to kind of place as many red cells as I can, and you kind of get these 2 patterns that naturally fall out, which are this pattern on the left here and the pattern over here on the right. Cool. So the problem with having 2 equality cases is that it's like hard to prove that they're equality cases if there are many different possible ways that they can come up, right?
Yeah, because your smoothing method is not going to work because you don't know where to smooth to, right?
Yeah, and the algebraic stuff. So we did a bunch of inequalities last time. It involved K and P, where K is the number of red cells and P is the number of red blue pairs. But that's not going to work here because that required equality in both these conditions that we use. And the conditions are just straight up not true for either of our equality cases here. Like in the first equality case, each red cell is adjacent to 4 blue cells instead of just 3. In the second equality case, each blue cell is adjacent to 3 red cells, not just 2 red cells. So we can't have both equality. Well, both equality cases can come true. They just don't end up proving the inequality that we want to prove. We have to go about this a different way. And the way
I have one question.
Yes.
I know this is, you might already talk about this. Do you still glue them anymore or no?
Yes. So the way you do want to think about this is by gluing red cells together, because the red cells have a pretty constricted possible like range of things that can happen. Like each red cell is adjacent to at most one other red cell. So this is where the idea of connected components comes in, and you can really get a handle on this problem. Is each red cell is either like this or like this, and it must be touching a sea of blues, right? So the way you kind of want to do this is to kind of prove this inequality. We can't really just resort to mindless algebra. We kind of have to like map each red cell onto its own blue cells, right? Because like basically the way you prove an upper bound here is that we're saying like each red cell is responsible or corresponds to a couple of blue cells, and we want to focus locally. And we want to say, oh, each red cell must be adjacent to must be touching the blah 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 blue cells, and therefore this is kind of bad. I kind of drew them too close together. Just imagine that there's a divide here. So we kind of want to like see how we can float these red components in a way that they're like as close together as possible.
James, what are you drawing? I can't see anything you are drawing.
Yeah, so I'm just saying that the red cells, there are 2 components. There are 2 types of components. They either have size 1 or size 2, right? Because each red cell is adjacent to at most one other red cell. So we either have this first scenario over here, number 1. We either have this scenario. I need to get my pen. We either have this scenario or we have this scenario. Do you understand that?
I can't see the pen.
Oh, can you not see anything I'm writing?
Oh, I can.
see.
I can.
Okay, so I'm drawing on the grid over here. So you either have 1 red cell that's adjacent to 4 blues, or you have a 2 red cell block that's not adjacent to any other red cells either. So basically, you want to figure out how you can tile a bunch of these red cells together so that like they kind of overlap these blue cells as much as possible. But we can't really correspond blue cells to red cells. So ideally, we would have each red cell biject to another blue cell, right? Does that make sense? So that we can map 1 red cell to each 1 blue cell. So they were like, oh, therefore we must have at most half of the red cells, because each red cell must be adjacent to 1 blue cell, must correspond to 1 blue cell. But the problem is that the blue cells can kind of overlap. That you might overcount the blue cells that you're corresponding to red cells. So there's a kind of a clever argument that you can come up with. And that's like, oh, if I can't correspond each red cell to blue cells, well, I'm going to correspond parts of blue cells to red cells. So I drew a slightly blown up grid here. And one key you could do is like you look at this red cell and you're like, oh, I need to like biject some blue area to it. So the natural thing to do is like you say, oh, well, I don't want to just biject the entire blue cells next to it because the problem is that that blue area might also correspond to another red cell. So you can kind of like divide up each blue cell into quadrants, or like kind of like it's kind of a quadrant if you see this.
But they
Right.
don't need to be geometric quadrants, right? You can just algebraically say you want to have 1/4 of each blue cell.
Yeah, it's a quarter of each blue cell. Sure. It doesn't even have to be the quarter that's closest to it. It's just a quarter of the blue cell. So nicely, like, so this is kind of like what happens here, and then like you can look at this, and if you can just like if you had let's say you had the checkerboard pattern over here that you see over here. Oh, that's not what I wanted. Checkerboard pattern over here. But then you would see that each blue cell would be divided into 4 quarters, and each quarter will biject to each of the 4 red cells around it. Does that make sense? It's a little bit confusing. So that's kind of how we want to go about doing this. We want to like divide up the blue area and like give it a red corresponding like representative. And in that case, we can come up with a bound. Otherwise, it becomes too messy because we're just overcounting blue squares here. So in the case of a connected component of size 2, we have something like this, right? And then we could kind of try to do the same quarter deal as before. That sounds nice in theory, but the problem is that here the red cells the red has area 2, but the blue has only area 1.5. So we still have an issue. The red doesn't really equal the blue right now. So how do we fix this?
Well, you make it
also
convex.
you also have the problem that those little inlets, as I want to call them, aren't being counted no matter what you do. So if you fill them in and make it like a hexagon, you should be fine.
Yeah, so David's right. You can also give this part of the area and count it too, which is nice. Now you have this perfect bijection. It's kind of a miracle. You have like a red cell, 2 red cells which have area 2, and then you can calculate the blue also has area 2, just because there's 8 quarters in it. So this is nice. So now in each of these 2 diagrams, I'm going to switch to a black pen now. You have that half the area is red and half the area is blue. So now our only job is that we have to tile the plane with figures like this. You have to tile the plane with figures like this so that you cover the entire grid. And this is still not tricky. So this, by the way, this second portion over here, you can also rotate this. So the hexagon can also be kind of a vertical version of a hexagon, by the way. So this part's a little bit trickier to describe. So how are you going to characterize like all the possible quality cases? Here you could kind of play around, but I think based on playing around, I think you can kind of prove that like you can't have both the horizontal hexagon and the vertical hexagon in your tiling. Is this true? I believe this is true. I haven't actually tried this.
Well, yeah, it's because if you have a horizontal hexagon, then above it you also need to have a horizontal hexagon, right?
So
that takes up the entire row.
The point of the okay, sure, right. So the point of a horizontal hexagon is that Alex is right. You must have a horizontal hexagon above it. So you take up the entire column. And if you ever have a vertical hexagon, you take up the entire row as well. So then they're going to intersect at some point, and that's bad. So
sorry. How are we, in terms of like making sure we tile the hexagons? Is this trying to maximize the number of reds?
So basically, like you try to maximize the number of reds, right? So you have to use these two. You have to tessellate the entire grid completely with these 2 types, because otherwise you're leaving some areas unmarked, and in which case you're not gonna have equality.
And if you show that once if you can tile them, then you know the answer has to be half or whatever.
No. So we've already proved the answer is 1/2. Sorry, if that's not clear. So we can do that. We can do this bound around each red square or red domino, and then that proves that it's at most 1/2 because these shapes can never overlap but just by looking at the way we drew the shapes. And because we're doing this around every single red shape, that means that we're able to correspond the blue area to the red area, and then there might be some leftover space, and if there's leftover space, all the leftover space is blue. Therefore, there's more blue space than red space. Does that make sense?
Right. Okay.
So the only way we can have exactly half is if there's no leftover blue space. So that's why we need to tessellate this entire grid completely. So Alex's argument is nice that we can't have a both horizontal and a vertical hexagon. So, well, obviously there's one. If we don't use either a horizontal or a vertical hexagon, I believe there's 2 ways to do it because it's just a checkerboard. You have 2 ways of coloring a checkerboard. Otherwise, you have 2 cases. You have a horizontal and you have a vertical hexagon. So let's say we have a horizontal hexagon somewhere in our grid, right? So we have an entire column of horizontal hexagons, which is nice. I'm not going to go over this too much because I do have a third part that I want to go over, and we're a little short on time. But the point is that you must end up having this entire chain that comes up, that goes on forever. Well, forever until it overlaps back over. Because remember that this entire grid is a torus, so the top and bottom edges are identified together. So now, once we have this chain kind of has width. I believe the width is like 3 of this hexagon. And then what do you do next to it? Next to it, you have another empty space right here. So what can you do? You can add one of these smaller squares if you wanted to, and then if you add a smaller square here, so this square represents here, then you can actually show that you must have an entire column of these as well, are all the same. And you do this by looking at the angles, because the angles, if you have the horizontal hexagon under it, then you have a 1 to 58-degree angle and 2 90-degree angles, and then you have a 30-degree angle left over, I believe. Yeah. Sorry, you have a 135-degree angle and 2 90-degree angles. And then you have a 45-degree angle left over, and you can't fit a shape in there. So if you have a thing here, you have to have this entire column just be a bunch of ones. Or if you don't do that, you'd have to have another entire column of horizontal hexagons. That kind of gives you an idea of how you can tessellate it. So then, at this point, the problem becomes a little harder. I can tell you what the kind of problem becomes equivalent to. The problem kind of becomes equivalent to taking a circle and trying to tile it with arcs of length 3 and length 2 under 2 more. And also, I believe you must also use an even number of arcs.
I think it should be lengths 2 and 1.
Is it 2?
1 with total
2 and 1,
300.
because the horizontal takes up 2 columns, the big tile takes up 2 columns, the small tile takes up 1 column, right?
Yeah.
I thought it was not 3 and 2.
No, I think it's 3 and 2.
It's 3 and 2. I
mean the width overlap, right? Like if you can see, like the zigzag is basically
oh,
the
my
overlap.
bad. Yeah, you're right. I actually originally did it with 2 and 1, and then I just changed it to 3 and 2 in the middle of this conversation because I thought I was wrong. So sorry. I was originally correct. It is 2 and 1, I believe. Yeah.
Math in a nutshell.
Yeah, obviously it's 2 and 1 because you can tile with only the hexagons and it works. Oh, my computer is lagging. Sorry, I can't write anything. Okay, there we go. My internet doesn't work. Huh.
You're talking right now. We're hearing you.
2 and 1.
That's good.
So sorry, I was incorrect this time. Yeah. So we tile with 2 and 1s. There's another condition. We also need an even number of arcs. Even number of arcs, and then we also want to multiply this answer by 2 afterwards, I believe, because we can translate everything up by 1 unit and have it also work and have a completely different tiling. So then we just want to, and this circle has length 1,000. I'm not going to compute this for you. It's actually not that easy. I think I would suggest the way to do this is to take one piece, focus on do casework on what a certain block is in, whether it's in a 2, of the left part of a 2, or right part of a 2, or is in a 1, and then you break it up into a segment of length 999 or 998. And then you start to do cases on the number of arcs. So then you have like a linear recurrence. I believe you have like 4 equations. It's not that nice, but you can compute the number of equality cases. But we've already characterized it to you for you, but if you want to compute it, that works. I believe that's it. Yes, sorry, you're right. It's 2 and 1, not 3 and 2. I realized that, and then I doubted myself. So thank you. So does that make sense? Is there any questions? Kind of. I thought this was kind of cool.
Well, James, I don't think you have enough time to go to the next part. Why don't you explain the 2 and 1 a little bit more instead of 3 and 2? I think that's maybe give people trouble.
Oh, so yeah. So instead of the reason why 3 and 2 is bad because 3 and 2. Actually, no. I was going to go over number 3 because number 3 is a similar argument to part 3 is similar argument to part 2.
Wait, someone mentioned that the length should be 300 because we've reduced the size of the square.
Yeah.
I
guess for this part, it doesn't really matter that much. It still works for 1000.
So the reason why I chose number that's divided by 3 is for part 3, actually. Which you guys should try it on your own. The connected components argument kind of falls apart because of certain reasons. Because the blues don't necessarily need to form like the blues can kind of loop around, and they aren't as restricted to the same connected component sizes as red, which is just 1 and 2. But you can still do a similar argument with the adjacent area sizes. And also the hint is that the answer is 1/3 for part 3. So we're gonna try that. You should try that on your own. We probably won't go over it next time because we've spent too long on this problem. But if you understood this problem, you'll definitely be able to get that with no problem. The reason why it's not 3 and 2. So originally I doubted myself and said it's 3 and 2 because the diameter here
is 3. Yeah.
The diameter. This pen isn't working. Okay. This diameter here. This is 3.
Yeah.
Well, the diameter here is 2.
Yeah.
But this
actually,
is kind
you only consider the red. Actually, it's 2 and 1. That's
so if you consider the red, it's 2 and 1. The 3 and 2 is bad because they overlap. Like this section over here just overlaps, and you're kind of overlapping. You want to do the 2 and 1. And then the reason why you can do the 2 and 1 is because you can consider each column separately because they're kind of independent. And once you have a certain square in a certain kind of tiling piece in a certain column, a certain part of the grid, you must have the entire column. That's that. And then once that's done, you can kind of see that the circle that I drew up here kind of represents just how you're going to tessellate the rest of the remaining columns of this grid.
Yeah.
And then the way you count something like this is, it's not that nice, but you take a certain part of it.
James, but why the number of arcs should be even? Sorry?
Huh?
Why the number of arcs should be?
The reason why is because if you look at the reds, this red here in this column must be here, right? And if you have an odd number of components that go to the right, left, and right, you're going to end up with so that the parity is going to end up wrong. So that you're going to loop this red. These reds are going to. I'm going to use a different color. Are going to loop like this, kind of like up and down. And then once you loop back around, you don't want it to end up here and have to have a red here. Does that make sense?
Okay.
So
you consider 2 adjacent rows of reds. Okay.
Yeah, right. So you see, I have a 2 and a 1 right here. This 2 represented by this arc, the domino size 2, and this red single square size 1. They're like kind of adjacent pieces in this circle of arc length 300, but in each column the tessellation is every other row. So you see that the parity is different here. So eventually once we loop back around, we need the parity to be the same. So that's why we need even number pieces. And remember, we have to eventually multiply our answer by 2 because we could also adjust everything down by 1, and that's going to give another set of answers, which are exactly the same number of solutions, but a completely different disjoint set of solutions, right? I'm sorry, I can't really write everything I want to here because, but that kind of makes sense.
You also have to multiply by 2 again because you can use vertical dominoes.
Right. So you have to multiply 2 again to go to do the vertical. Also, when you saw the 300, you also have a restriction that you must use the green 2 at least once, right? Because only horizontal. Alternatively, you can not use that restriction, just subtract 2 because you're going to count the chessboard tessellations twice. So alternatively, I would just recommend just forgetting the condition that you need at least 1 horizontal, just subtract the chessboard tessellation for overcounting it for both the vertical and the horizontal. It's a little bit tricky of a counting problem, but it's kind of cool. So you're going to have a gazillion equality cases, It's definitely a very interesting problem to think about. Unfortunately, problem 3 is not as interesting in terms of equality cases, but I think proving the bound is a little bit different, although the idea is similar for the third part. I can go back and show you what the third part was, which is to find the minimum number of red cells.
I think we are okay. Well, I think let's stop here, James. It's about 9 o'clock. Okay.
Oh yeah.
Let's stop our show here. But I think we had discussed 3 wonderful problems, and the people can go home and digest a little bit all the little details. Okay. Why do you multiply by 2? The verticals and the overlapping here. That's a very, very good counting, right? Mm-hmm. Okay. So let's stop here. Everyone, good night.
Mm-hmm. Good night, everyone. See you next.